Thank you, Zoom. All right, so this week and the rest of today's class and the next class, we need to go over section 6.3, 6.4, and 6.5. In 6.3 and 4, we're going to take a closer look at difference in proportions. And that's for two populations. And in 6.4, we're going to look at a difference in means for two populations. And we've done this with StatKey's help. We're going to learn how to do it on a spreadsheet next. And then 6.5 is actually the easier of these right here. It's a difference in means for paired data. I'll explain the difference between 6.4 and 6.5 later. That's an A in there, believe it or not, for paired or matched data. So examples of the paired data that we saw before would be the husband's versus wife's age that we looked at before. Another one that we looked at was the pulse rate, quiz versus test. And these are paired because the husband and wife are a couple, right? My wife is Michelle, and she is a year older than me. I don't have a different wife. And as far as the pulse rate is concerned, we're not comparing my pulse rate to your pulse rate. We're comparing my pulse rate on the quiz to, that was supposed to be my pulse rate in class, regular class there. So sometimes data is paired. Sometimes it's not paired. For example, we have a group of mice who are given this young blood transfusion. We have this different group of mice that have an old blood transfusion. Those are two different populations, and we have to treat those two cases differently. And it turns out the 6.5 stuff is the easier stuff. So this is the easier kind of thing to do, because it's really not much different than the regular mean stuff we've done. So we have done this stuff before, we just haven't seen the formulas. So we're going to start off with section 6.3 today. Might get to 6.4. I think that's probably going to be the next class. So for a difference in proportion. So the key here is we have two populations. Two populations mean we also have two different samples. So in sample 1, we're going to have to keep track of x1, the number of successes from that sample, and the sample size for that sample. And then we're going to have this other sample, sample 2, and we're going to need to know how many successes were in that sample, whatever we mean by success in that situation. And then how big is that sample? Then we're either making a confidence interval or we're going to do a hypothesis test. So I'm just going to throw out the formulas and then we'll try to apply them in just a minute. As far as, let's see, we'll split the screen like we did before. For a confidence interval, at first glance, it's not too much different than other confidence intervals that we've done. I need to find my sample statistic. And since this is a proportion, I then need to add or subtract that magic z-score times whatever the sample error is. So we have to figure out if there's two proportions, how do I come up with a sample statistic? How do I come up with that standard error? So remember, standard error is a standard deviation. And we already know how to find the standard deviation for a proportion. So for each of these guys up there, I would have to find my p hat. So p hat 1 would just be x1 over n1. P hat 2 would just be x2 over n2. So we can find those. Once we have those, well, the sample statistic, if it was a single one, would just be p hat. Now I'm looking to see if the two proportions are different. Generally in math, different means subtract. And so typically the sample statistic is going to be p1 hat minus p2 hat, whatever that difference happens to be. And we'll look at an example of this in just a sec. Z-score, same as before. We use an norm inverse or StatKey to calculate that. Now the standard error, prior, if there was just a single sample, the standard error for a single sample was that p hat times 1 minus p hat over n, all inside the square root. But I need one of those here, and I need one of those there. And standard error is a measure of how spread out the data is. So we have to take the spread outness of sample 1 and combine it with the spread outness of sample 2. That means I have to add their spread outness together. And the way we do that for the standard error, I'm just going to write SE here again for now because the formula is kind of nasty. The standard error is basically start finding the standard error for sample 1. So that would be p1 hat times 1 minus p1 hat over its sample size n1. Now usually we would take the square root right away, but it turns out we don't with two samples. First we combine that with that fraction for the sample 2. And then after we add them up, we take the square root. So little messier formula. We can put it into a spreadsheet. Once that's typed into a spreadsheet, all I have to do is type in x1, n1, x2, n2, and then the spreadsheet's going to go whoosh and calculate this other stuff. We just have to make sure we type this right into a spreadsheet. I'll show you how to set that up next. And again, the z-score is just like the z-scores from before. If I use a spreadsheet, that z star is going to be the opposite of the norm dot dist, whatever alpha over 2 ends up being, 0, 1, true, which is what we've done the last couple weeks now. This is our 3rd week trying to use that formula there. So that's confidence interval setup. We'll do one in just a second. Formula I need here is, again, kind of similar to before, right? We got to find a sample statistic. That's the difference in the two proportions. Otherwise, our margin of error here is the same as before, z-score times standard error. And the standard error here is a bit wicked, but it's doable. Would I have you memorize this? Absolutely not. We'll look it up whenever we need it, or grab it out of the spreadsheet. Hypothesis test. So for a hypothesis test, so that's a situation where we have some previously known knowledge, the null hypothesis. So H0. Now the null hypothesis for a difference is usually, there's probably not a difference, right? The difference is 0. So we can write that in a couple of ways. The P with a subscript D, that's the difference in proportions. We just say, hey, you know, there's no difference. Difference is 0, no difference. Other way we could state that, which is more common, is we say P1 is the same as P2. Right? And either of these mean there is no difference. Right? AKA the same. And the alternative hypothesis is either one's bigger than the other, one's smaller than the other, or they're just not equal. And we'll worry about that later, but knowing the null hypothesis is important. And this P difference, by the way, right, it just means, oops, it's supposed to be a D, is P1 minus P2. Like I wrote over here, but with the hats. One of those guys missed his hat. It's been blown away in the wind yesterday. All right, so we have a hypothesis. We also need to have a significance level as usual. Otherwise, we need to know the standard error and the sample statistic, and we need to know the test statistic. And so this one right here is also a bit of work. So the test statistic is going to be a z-score, because I have a proportion. And it is going to be a summary statistic from P1 and P2, I'm just going to call P hat, minus whatever we say P difference is, divided by the standard error. Okay, now here's the catch about this P hat. Like, normally what I write here is what I call the sample statistic, right? Well, the sample statistic is, for a confidence interval, is P1 hat minus P2 hat. However, I got a problem, because the null hypothesis says they're the same. What happens if you subtract a number from itself? Like, suppose we say the proportion is 1/2. What's 1/2 minus 1/2? It's 0. And that's a problem, because I'm going to have a 0 here, a 0 here, and a 0 in the denominator, and everything falls apart. So what we do instead is say, okay, we're assuming they're the same. So if they're the same, then that means P1 is equal to P2. So this whole x1 over n1, x2 over n2, they should be about the same. So we think about it as a batting average, right? So I went x1 times up at bat this week. Next week, I'm going to go x2 times up at bat, and I divide that by the total number of times for each try. Oops, that's supposed to be an n1 there. So this is called a pooled proportion, and it's just a batting average. So again, the null hypothesis says there's no difference in these proportions. So we just throw it all together. Take the total number of successes, x1 plus x2, divide by the total number of trials. And again, that's because we assume the null hypothesis is true, right? Otherwise, we're just saying the difference is 0, which isn't very helpful for the test statistic. We won't get any answer out of it. So that's how we get P hat. This is called the pooled proportion. And that's what we use to get the standard error also. So the standard error for a hypothesis test is that pooled P times 1 minus it over the first sample size plus that pooled P times 1 minus it over the other sample size, all inside the square root. So we're going to try to do both of these on some data. Let's do it. All right, so I've got this data about ICU admissions from a certain hospital, and there are 200 different patients here. All kinds of things were recorded about these patients. The two I'm going to focus on are the status. So status is if they live or they die after being submitted to the ICU. So a 0 means they lived, and a 1 means they died. The other thing I want to look at here, the two populations I'm going to look at, so the proportions. What's the proportion of people who lived? What's the proportion of people who died? And then I want to base that on the population. When they got to the ICU, did they have an infection or not? So 1 means they had an infection, a 0 means they did not have infection. So I'm wondering, is there a difference in the proportion of people who died that came to the ICU with an infection versus the portion of people that came into the ICU without an infection? And I summarized this data on the next page here. So I just copied over, I kept their IDs to make sure I didn't screw up sorting things, and I sorted them by status and then infection. And so you can see here, I have a whole bunch of people who lived and did not have an infection. And as I scroll down, eventually I see the people who lived and did have an infection. And then eventually I see that all the ones, the people who died and didn't have an infection and died and did have an infection. And I asked the spreadsheet to count them all up for me, and that's what's in this summary table here. So let me bring that into my screen so we can figure this out. All right, so here's the setup information. I just kind of spoke it all to you. I'll read that back to you in just a second once I copy my table in. So I just need the summary statistics. I don't need the raw data here. And we'll look at this in a couple of different ways, using those formulas and then using a randomization. So add to current page. All right, so what are we doing again? We've got ICU admissions data, and we have two variables. The status variable indicates in the intensive care unit whether the patient lived 0 or died 1. And again, I had the computer count those up. The other variable was, did the inpatient arrive with an infection or not in the ICU? And so then we have 1 for yeah, they had an infection, or 0 for they didn't have an infection. And I told the computer to count all the zeros and ones in the right order. And then I have some totals here. So if we look at the infection row here, there was altogether 84 people in the ICU out of 200 that had an infection, and 64 of them lived and 24 died. In the ICU, from these 200 people, 116 of them had no infection, 100 of those lived, and 16 of them died. And what I'm concerned about here is the proportion of people who died, whether and if they had an infection or not. So my two populations are, population 1 is, did they have an infection? So this is population 1, and the no infection, that's my population 2. And from those populations, the parameter, the thing I am measuring, P, is how many died out of the total. And I want to know that for population 1, I'm going to call that population I for infection here. So 24 of those people died out of a total of 84 people in that population. My other population is population no infection. Let's call that P sub n here. And 16 of them died out of 116 total. And then the thing we're going to look at here is there what is the average difference in these proportions? PI minus PN. So we're going to do a confidence interval first. So 95% confidence interval for the proportion with an infection that died minus the proportion without an infection that died. PI minus PN. So this right here is my sample statistic for the confidence interval. Statistic. It is also my point estimate for the interval. So the first thing I'm going to do is I'm just going to run the StatKey and say, StatKey, can you randomize this for me and give me a quick answer? And then I'm going to try the formula to see how it matches. So in case you want to check out the spreadsheet, I'll share this. You really don't need the direct spreadsheet. We're going to use StatKey first. I guess we'll come back to this after. All right, and then StatKey, what we want to do here is, let's see, what do we got? We got a proportion, but it's a difference in proportion. So I need to make sure I'm in the right place. So confidence interval, difference in proportion. I want this one right here. So that in the chat too, and in the YouTube video description. Now, my ICU data is not in here. There's a bunch of other cool data. So I have to edit mine in here. And all they want is the count of my two groups. And the order matters. And so my first one, let's see, where did that spreadsheet go? Over here. Let's pull this over so I can see the numbers to type them in. All right, first one, group one, I was saying, was the group in the ICU with the infections, and 24 out of 84 of them died. In the group in the ICU without an infection, 16 died out of 116. And then StatKey calculates what P1 hat is, 0.286, and group 2 is 0.134. So it looks like, you know, about twice as many, that the proportion of people who died with an infection is twice roughly the proportion of people who died that didn't have an infection. So we gotta wonder, whoa, that's huge. It's almost double. Is there a difference? There seems to be a significant difference. We're gonna have to come back to the hypothesis test to see how significant it is. Once we get that data in StatKey, we just go bang, bang, generate thousands of samples. So did I change the sample size? No, the sample size is still 84 and 116. I just made 7,000 new samples of 84 and 116, where I mixed up the patient's records a little bit to see what kind of variation I might end up with. And this is what StatKey says the variation is. What did I want for a 95% confidence levels? Then we just say StatKey, two-tail. StatKey says, how about 95%? So StatKey says the difference in ICU patients all over the place should be somewhere between 3% and 26%. So notice a difference of 0 is not in this interval. So that kind of heads toward the hypothesis test. This seems to be significantly greater than that one. There does seem to be a significant difference, but we're just coming up with an interval. So we think the difference between the proportion of people who die that had an infection versus the proportion of people who die who didn't have an infection, that difference is somewhere between 3.2% and 26.2%. Just gonna grab a screenshot of this, then we'll try the formula, see how similar it comes out. All right, so here's the StatKey version, and I guess that needs to be on a new page. All right, so we'll come back to this in a second, but we have an estimate of the confidence interval from StatKey. Next, I'm going to try this on a spreadsheet. So instead, let's see, I want to have everything that's important in one spot. So we're going to go back to that spreadsheet I've shared in many other videos. This one right here, right here. So this is my inference examples from chapter 6. We're still in chapter 6, so I'm just going to keep adding to this. So if you grabbed a copy of this earlier today, you might notice that way off on the right, I have a couple of 2 proportion tabs, 2 proportion confidence interval and a 2 proportion hypothesis test. So I'll walk through how I set this up, and we'll try to use it for this problem right here. Reshare this for anyone who's missing it. Copy. All right, so this again is that chapter 6, all kinds of problems. This will solve almost any problem from chapter 6 on some tab here if you pick the right one. So I'm on the tab way over at the bottom on the right, 2 prop CI, so 2 proportion confidence interval. Title at the top says a confidence interval for a difference in proportions. So in here, I need to say what's my confidence level, and we were setting that to be 0.95, 95%. And then I need my sample data. So in this case, these would be my infected population. Infection. And then the second group here would be my no infection. I find I have to write these notes to myself all over the place, otherwise I'm easily confused. Then I need to enter the data. So my data here was that 24 out of 84 people with an infection died in the ICU. And then the other group, 16 out of 116 of the people without an infection died. And then down below, I have my spreadsheet make the calculations. So p hat from the infection group, let's see, label here, proportion of patients died. That's that one. Let's grab this one. Proportion of patients who died without an infection. Oops, I missed the N on the end of that one. This one is capitalize that to stand out. And so all it does is it just looks above and it says, oh, let's take x1 over n1, x2 over n2, and then down here we just subtract the two of them. So this one right here for our confidence interval, this is what we call the sample statistic, the difference in the two. The standard error takes that big nasty formula and just puts it in a spreadsheet. So it just says, you know, take this P1, 1 minus P1, divide by the sample size, P2 times 1 minus P2, divide by the sample size, take the square root. So all I'm doing there is just I typed in the right order of operation. And, this formula right here. Ah, that one right there. And then after that, we just find our alpha and alpha over 2 to get the magic z-score. Margin of error, remember, is the z-score times the standard error. And then we just add and subtract that to the sample statistic. So this one down here is the sample stat minus the margin of error. This one is the sample stat plus the margin of error. And does that match what the StatKey simulation gave us? 0.0326, StatKey said, StatKey go? There it goes, 0.032. So it doesn't have that fourth decimal place. And then 0.262 versus the spreadsheet, 0.263. Notice they're very close, but again, the randomization is going to be different every time. This is a theoretical approach, kind of like saying, hey, when you flip a coin 1,000 times, you're going to get about half heads. So this is the theoretical approach to it. Notice the StatKey randomization approach is a lot easier, but there's sometimes we just can't use it, and we got to throw out the spreadsheet version instead. So nice thing here is we have a spreadsheet where we just enter confidence level, sample data, and then the spreadsheet makes all the calculations from the formulas. And we have to interpret it. So more on interpretation in the next class.